No. No. It was super weird. Okay, so yesterday's assignment was to learn about how to name covalently bonded compounds. I apologize. I guess the sound wasn't very loud, but it's also in your book. Always look in your book. Chapter 9, Section 3, if you need a review. It's pretty simple stuff. I think everything's simple once you know it, so forgive me if you didn't think it was simple, but covalent compounds, that worksheet, quote unquote worksheet, it was Google Slides, I asked you to work on. And then we're going to talk a little bit more about the end of Chapter 8. We're not going to get very far. I'm going to talk to you about oils today and how they fit into the schema thing. And then there's a review that should be in your feed. And then tonight, you should have 5 or 10 minutes towards the end to get started on the online review on sciencegeek.net. There's a document that should be coming in. And Thursday, there'll be a quiz on naming compounds. Okay, so lots to get done today. Not the day for technical difficulties, but whatever. Just roll with it. That's all we can do, right? It's, yeah. That one. Let us, that's not what I want. I want to go to this and take a peek. So looks like, hey, you guys have got the most people got their homework in, or their schoolwork for yesterday in, since it was technically a school day. The other classes had a much lower completion. So again, good job, 6th period. And this is the worksheet with the little fill-in boxes. Binary molecular compounds are composed of what, Julian? Question number 1. This is yesterday's work. Binary molecular compounds are composed of 2 what kind of elements? What are the 2 categories of elements? Well, I guess technically there's 3. Yeah, so binary molecular compounds are 2 nonmetals. So there's metals on the left, metalloids on the zigzag, and nonmetals on the right. And these are 2 nonmetals. This kind of compound, as with other binary compounds, and with what, Michael? It is IDE. And prefixes tell us what? Galilea, what does it prefix tell us? Like carbon dioxide. What's the di tell us? Number of atoms. Okay. How many atoms of each element? And then how would you name this one? Jack Conte. Arsenic pentasulfide. Beautiful. So AS is arsenic. And before I forget, who needs a periodic table? Does everyone have one in here? Okay.
Yeah, it like disappeared within the first week.
Disappearing periodic tables? Really? Is this magic? Fortunately. Yes. No. It's great if you don't. It's fine. Periodic tables.
I'm pretty sure. I don't. Thank you. I don't. Do I need one today?
No, we've got them in there.
Because I have one at home.
Okay, that's fine if it's at home. I just want to, if you don't have one, some people didn't get one. Did you get one, Nathan?
Yeah.
All right. So AS is arsenic. People in first period couldn't come up with that. And then S, of course, is sulfur. If there's a subscript on the first element, you have to have a prefix. If there's not a subscript, we don't use mono for the first one only. All right, our true and false. This book does it always true, sometimes true, never true. Binary compounds contain carbon. What do you want to say about that, Gwen? Sometimes true, absolutely. Charges must be balanced when writing formulas for molecular compounds. How about Haley? Never true. Okay. Charges are only for ionic compounds. And they have to have equal positives and equal negatives to get to 0, but that's not true for covalent compounds or molecular compounds. And then CO2 is named monocarbon dioxide. What do you think, Taylor? Never true. What is it? Carbon dioxide. This plain old carbon dioxide. Okay, and then matching for 8. What'd you get for binary molecular compound? Bethany? Non-ionic compound 2 elements. How about Colin? What'd you get for 9?
8.
Absolutely. How about number 10? Oh, Taylor, it's your lucky day. Yep, and that must leave C for tetra is 4. All right. How would you name 12A? Let's pick Aiden. What's P?
Phosphorus,
What's Cl?
chlorine.
Okay, so there's 1 phosphorus and 5 chlorines. Good, good. Name the first element. Good. What's the prefix for 5? Like where the military is in Washington, D.C. And Cl is chloride. Phosphorus pentachloride is the answer. How about for B, Caius? What's S?
Sulfur dioxide.
Perfect. And then last but not least, Michael, P4S10.
That,
6 for 4.
Tetra, it's a 4.
Oh, tetra phosphorus.
10 years is a decade, so it's decasulfide.
So it's
Tetra?
Tetra phosphorus. Tetra's 4.
Okay.
it's phosphorus. I put phosphide.
No, it's only phosphide if it's at the end.
Okay.
Okay, so the first element gets its real name. The second element's ending goes to ide. Like sodium chloride, you know.
Yeah.
Okay, and then what's the formula? I'll just pick on Logan. What's the formula for carbon tetrabromide, do you think? Guess, what's the symbol for carbon? C. And bromine. Br. Yep, so what's tetra? Mono, di, tri, tetra. Tetra is 4. So the formula is going to be? Okay. Dinitrogen tetroxide and Gabby. Nice. All right, any questions on that? Okay, so we'll put that away. Any questions from the home front? All right, let us talk about oils. So the reason why we're going to talk about oils is because one of the substances we're going to use in our penny lab tomorrow, yet another penny lab, is oil. And so we're going to use water. We're going to use isopropyl alcohol at a higher concentration of alcohol than you can buy. And we're going to use vegetable oil. And we're going to see how many drops you can put on the surface of a penny. You should know by now that water has a bent shape. Water has oxygen and 2 hydrogens, duh. And water is sticky. Remember on the Friday, was that the 26th? Before we went on vacation, we watched a little video about the little skeeter bugs walking on water and stuff. And that's because water is a very, what kind of molecule? Polar or non-polar? No. Polar. Oh, I was going to say this for tomorrow, but maybe. I just spilled water on your desk. Sorry you couldn't see that at home. It was really good. So water is very polar. Oh, except when it falls apart. Water is very polar, right? It sticks to itself. Okay, and it is because of the 2 lone pairs on the oxygens and because of the bond inside of the molecule as well, the intramolecular bond between hydrogen and oxygen, very polarized, right? The electrons are being pulled to the oxygen, making this more negative, making the hydrogen more positive. They want to stick together. Even though the molecule's neutral, they still are sticky. Isopropyl alcohols. Alcohols are a little bit sticky, barely sticky, not as sticky as water. And then plant oils are non-polar. So let's find out. You guys, anybody new use essential oils at their house, like in a diffuser, little drops and stuff, right? They smell good. They can make you relax, help you fall asleep, all sorts of things. Don't know how scientifically proven they are, but they smell good, right? So how do we get those oils? This little quick video tells you about it. Hopefully the volume will play. I swear to God, every period has been something different.
In this lesson, we will learn about plant oils, where they come from, how to extract them, and their generic structure. These oils are found in all parts of a plant: seeds, nuts, fruit, leaves, flowers, bark, and even roots. However, these oils must be extracted before they can be consumed or used. There are a few key methods to extract plant oils: mechanical extraction, distillation, and steam distillation. Olive oil is obtained from olives by mechanical extraction. This method is also known as cold pressing. The olives are crushed and pressed to squeeze all the oil out. In the past, these heavy machines were operated by humans. Nowadays, most mechanical extraction is done in a factory by machines. Coconut oil is also obtained using this method. Note that these oils are essential cooking ingredients in certain parts of the world. Some plant oils, such as sunflower oil and soy oil, are obtained by distillation. These oils are first dissolved in a solvent, and
So hexane, hex means 6. So there's 6 carbons in hexane. That's a common solvent. And then the ANE means it's all single bonds.
solvent is removed via distillation. Most impurities are also removed during this process. This method is used for oils that are more difficult to extract from their respective plants.
So you guys remember I had the distillation set up here first semester. I think I just filmed it for you when I was doing the separating of mixtures with everything. We heat this flask where the liquid is, and then the gas goes through that center tube, and then the jacket around it has cold water coming in from the bottom, and then that cold water is warmed, but it causes the gas to cool, which causes it to condense into a liquid here.
Steam distillation is used to extract floral oils, such as rose and lavender oils. Steam is passed through the flower petals. The oils are then able to evaporate. Since the oil droplets are very small, they can form an emulsion with water. The oil can then be separated using distillation. We will now look at the general structure of plant oils. The structure can be broken down into 2 parts. First, we have the glycerol head, which is hydrophilic or water-loving. This head is made of 3 carbons.
So Philadelphia is the city of love, right? Phila has to do with love from the Latin. So this side of the molecule likes water, and the other side doesn't like water. What's hydrophobic, right? If you have a phobia, you don't like things, okay? It doesn't mix. And the reason why it doesn't mix with water is because it's non-polar. Water's polar, oils are non-polar, and you all know that oils float on water. That's because of their density, but they also don't mix, right? You can shake them up. Your Italian salad dressing, if you make it from scratch, you can shake it up, but it's not going to stay mixed together. It's going to eventually separate, and that's because the oil's non-polar, the water's polar. And so we use a phrase called like dissolves like. Things that are polar or ionic dissolve in water. Things that are non-polar will dissolve in oils. And we'll talk more about that tomorrow.
These 3 carbons are each attached to 3 fatty acid tails, which are hydrophobic or water-fearing. The length of the tail can vary from oil to oil. It can be anywhere from 4 carbons long to 28 carbons long.
So each of those little fingers of the hydrocarbon, they're the fatty acid, they're all these carbons in a chain. And you remember when we built our molecules that the carbons don't go in a straight line like that. That's how we draw it on paper. But when you're dealing with carbon, right, the tetrahedral bonding, it causes it to zigzag. So in reality, the shape would be something like this, where, and organic chemists are super lazy. They don't write in all the C's at all the apices, but you're supposed to understand that those are carbons. So it's going to zigzag, but this other line's going to be zigzagging too. And those 3, not very good drawer, those 3 chains, okay, can sit on top of each other if they're all single bonds. Yeah.
Where do the hydrogen? Where do those sit on?
So the hydrogens, it's hard to do on, that's a really good question. So every carbon has 2 bonds already to another carbon, or these end ones go to oxygens, but there'd be, so this is 1, 2, carbon to carbon, and then like that. And it gets really tedious to draw in all those hydrogens. So that's why you'll just see, you're supposed to, that's a molecule. Okay, and it's got carbon, 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 carbon. That's hexane. But then you got to put in all the flippin' hydrogens, and it takes for flippin' ever. Which you can understand why they stopped doing that, right? Yeah. Okay, so yeah, it's one thing if you can cut and paste on your computer. It's another thing if you have to draw it all out. Okay, good question.
These tails can be saturated or unsaturated. The term saturated means that there are only carbon-carbon single bonds. Saturated plant oils are solids at room temperature and are also known as vegetable fats.
So fats tend to be solid, whether it's lard, whether it's vegetable fats, cholesterol, right, animal fats, are single bonded, saturated. They're holding all the possible hydrogens that they can. But if I decide to make a double bond between the 2 carbons, here, I'll pick this one. If I decide to do a double bond between the 2 carbons, hydrogen, 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 hydrogen. If I want to make a double bond, then I have to get rid of hydrogens, because this one and this one need to make that double bond. So that's what's called unsaturated. It could have more hydrogens on it. And these saturated ones tend to be solid at room temperature. Unsaturated ones tend to be liquid at room temperature. She's going to tell you that in a minute.
An example of a saturated plant oil is palm oil from oil palm trees.
So this is used a lot in cookies and things like that. And there's a real environmental issue with getting palm oil and destroying the habitat of orangutans in particular. And so if you see stuff about people protesting Girl Scout cookies, it's because of how the palm oil is harvested and the destruction to the native habitat in some places. But this tends to be a solid.
The term unsaturated means that there are carbon-carbon double bonds somewhere within the structure of the fatty acid tail. A monounsaturated oil has only 1 carbon-carbon double bond. A polyunsaturated oil has more than 1 carbon-carbon double bond. Most unsaturated oils are liquids at room temperature.
So these are supposed to be the good oils for you. Avocado oil, sunflower oil, olive oil, or unsaturated fatty acid, have unsaturated fatty acids. They have double bonds in those arms. And so these make kinks in the little arms so that they can't lie flat next to each other. And that keeps them from becoming solid. That's why they're liquid. You're probably all too young to be worrying about this, but maybe your parents or your grandparents talk about unsaturated, polyunsaturated oils, and they use those in their cooking. And those are the ones that have these. And so you'll hear about omega-3 fatty acids. What does that mean? Alpha and omega, beginning and the end. Okay. The end is the omega. And so if you count back 1, 2, 3 carbons, the third carbon from the end has a double bond. That's an omega-3 fatty acid. Okay. And different types of plants make different kinds of oils. And then if you go to the 6, this would be an omega-3 6 fatty acid. Omega-9 fatty acid, they can do that. Flaxseed oil has that in it. So those are all, some people take those as dietary supplements because they helps their skin, helps their eyes, all sorts of things. Fish oil has lots of omega-3 fatty acids. Yep. And so that's very good for you. That's why, you probably don't. You guys are back in the old days. Cod liver oil was a big thing. I guess it's kind of becoming popular again. So they just take the fish and squeeze the oil out of it. Ew, out of the liver. Ooh. It's good for your skin and your hair and your nails, and it tastes like crud.
Yeah.
Okay, fish oil. Ugh. Even the stuff that says non-burp. It's awful. Take flaxseed oil. It's good.
There's like capsules too. There's like pills that you can take it in, but they're like huge.
Yeah, it's like, what am I, a horse? Come on, you guys. Yeah, but that's where those terms all come from. It has to do where the double bonds are in the chains.
These unsaturated oils can be hydrogenated through a process called hydrogenation. This hardens the oil and is a key step in the production of margarine.
So what do? They take the good oil and they infuse it with hydrogen gas, break the double bonds, and make it a bad one. That's how you get it, so you can spread it on your toast. Instead of, I'd rather just dip my French bread in my olive oil and balsamic vinegar. But if you want to spread some on your toast, it needs to be a little bit solid. And so different margarines, if you've tried different kinds, some of them are hard as a rock when you take them out of the fridge, and some are softer. Those softer ones probably will turn into a pool of oil if you leave them out of the fridge too long. But that has the better fats in it. Yeah.
So if you're still putting it back into like the bag form, does that make a difference?
Yep. It makes it not as good for you. Yeah. So
there's no real difference between margarine and butter,
other than margarine sourced from plants as opposed to sourced from a dairy cow. So there's also arguments about, what is less impactful. That's a good word. Thank you. So butter got a really bad label in the late 60s, early 70s. And there are people that put butter in their coffee now, right? Yeah. Keto diet. Okay. Because bacon's good for you. I don't know about that, but I don't know. You can, always going plant is going to be less impact total start to finish, but it also doesn't taste as good as bacon. What are you going to do, man? It's terrible. Sorry, Mr. Pig. Okay.
In the laboratory, one can differentiate between a saturated and an unsaturated oil by testing with bromine water. An unsaturated oil will decolorize bromine water, whereas a saturated oil would not. In summary,
so let me just stop there because that was a really bizarre thing that they just threw into this video without any explanation. So bromine, what family is bromine in? Halogens, good. So chlorine and fluorine, bromine and iodine, those are all the very reactive halogens. Remember, they just need one more electron. What they end up doing, bromine's a liquid at room temperature. It's brown. What they end up doing is they put a little in the water, turns the water brown, put the unsaturated fatty acid in there, and the bromine breaks the bond, and the bromine comes in and bonds in place of a hydrogen. Okay, and so it pulls the bromine out of the water and puts it into the fatty acid. And, you know, not every single space is going to get bromine, but that's why the color goes away, because the bromine's not in the water anymore. It's stuck on the fatty acid.
Plant oils can be obtained by mechanical extraction, distillation, or steam distillation. All plant oils have the same generic structure: a hydrophilic glycerol head and 3 hydrophobic fatty acid tails. The fatty acid tail can be saturated if there are only carbon-carbon single bonds, or unsaturated if there are carbon-carbon double bonds present.
So the saturated ones are basically straight. They have the carbon backbone, but they can pack on top of each other. And so that's what allows them to become solids. This end is basically non-polar. Okay. It doesn't mix with water. This end is polar. It's hydrophilic. This end's non-polar, hydrophobic. And that's why the oils, because bulk of it is non-polar, is going to not mix with water. All right. So a lot of information there. Hopefully some of it useful to somebody. What else did I want to show you? This is in your feed, and somehow, I don't know if it's Google Chrome, can't figure out my new computer either, but on the slideshow that you did for homework, for yesterday's schoolwork, I did the exact same process. The boxes were nice and small. This one, to make the boxes small, I had to make the font 3, which is invisible. So I don't know. I'm still trying to figure out what the heck is going on here. But this is just a review of stuff we've already gone over. So intramolecular bonds are the covalent and ionic bonds that you've learned about. Remember, in ionic bonds, excuse me, let me go back up here. This is how atoms stick together to form compounds. Ionic bonds happen when a metal and a non-metal are attached to each other, and that's because the non-metal steals electrons away from the metal. Covalent bonds, like hopefully you learned yesterday, are from 2 non-metals. Top right-hand corner of the periodic table. They share electrons, but they might not equally share. That's the polarity thing because of electronegativity. And electronegativity is how the atom pulls on the bonding pair of electrons. And remember, nonpolar have a difference of 0 to 0.3. Polar has a difference of 0.4 to 1.9. Ionic bonds are a difference of 2 in electronegativity or greater. So greater than or equal to 2. The intermolecular forces are the forces between molecules. That's how molecules stick together to form liquids and gases. But if you try and type in that, it's microscopic, and I don't know why. So I can make it bigger, but then the box occludes everything else. So anyway, this is how we form liquids and solids. Polar molecules have dipoles. They have slightly positive and negative ends because of the bonds inside them, like between hydrogen and oxygen, or because of, and that says geometry. Okay, so I make that really big. It doesn't fit, but the geometry of the molecule, and that's usually because of the lone pairs. And again, this is for you guys have polar bonds inside of them. So nonpolar molecules can have polar bonds if their geometry is correct, equal tugs in all directions. Okay, the molecule will be nonpolar. And then the forces that we're going to investigate in our lab are these dipole-dipole forces. The strongest one is hydrogen bonding. And then the instantaneous, momentary, temporary dipoles caused by dispersion, movement of electrons. Anyway, that's dispersion and that's electrons. Ha ha ha. It's not just a blue line. I'll try and fix it tonight and see if I can get it so it is visible. All right, you have 5 whole minutes. If you look at this practice sheet, it's also in your feed. And there's 6 questions total. The first 4 ask you a little bit, first 3 ask you to answer, and then the 4 and 5 are these quizzes. So this is on the sciencegeek.net site that we've been on before. One of them is on writing ionic compounds, and one of them is writing covalent molecular compounds. Both of them are binary, just 2 elements. And it's pretty straightforward. The only thing I just want to warn you about on this one, super particular about spelling. If you spell it wrong, you will get marked wrong. So N2H4, how would we name that? What's the sub 2 tell us? Di, what's H? Oops, that's not an H. And then what's 4? Just hydride. And I got a J on there. It would probably tell me it's wrong. Let's get it right. Hydrogen, dinitrogen, tetrahydride. Yay. Yeah.
So for the I that Jack was saying earlier, it's only if it's on the last word.
Yep,
Like,
the last word, like sodium chloride. Okay. Carbon monoxide. Carbon dioxide. Phosphorus pentachloride. We did that one earlier. The tricky ones, and I did this on purpose, are the ionic ones. You got to pay attention to where they are. Sodium's a metal, has a +1 charge. Sulfur is a nonmetal, it has a -2 charge. To get to 0, you need 2 +1s with 1 -1, right? The crisscross thing. And potassium oxide, same thing. Potassium's a +1, oxygen's a -2. Do the crisscross for the subscripts. Notice there's no prefixes in the name because you don't need it because they only ever have those 2 charges. Okay. Questions on what to do on those? All right, so that's what I'd like you to do, is to do that for homework tonight and have it before class. Yes, sir.
Is it pento or penta?
Oh, good question. So 2 vowels together don't go well together. So it's penta with oxygen or something like that. It would do pentoxide, would drop the A. So you tend to drop the A's and keep the O for oxygen. But it's penta with chloride.
Thank you.
Any other questions from the home front?